Here I'm going to briefly discuss what a purge stream is and why we would need it in a system. So it's a system where we have recycle. So we have a recycle stream because all of our reactant did not react. So for example, if we have A and B fed into a system and in the reactor A plus B goes to C, and we're able to separate out C and recycle A and B. So A and B is recycled. However, if, for example, there's also an inert in the feed stream, this inert's not going to react, and if it's not separated out, it'll be in this stream, so it'll be in this stream, which means we have to have a purge stream, or this inert concentration would just keep increasing since it doesn't react. We cannot reach steady state. So we must have a purge stream so that the molar flow rate of inert leaving out of this system should be the same as the molar flow rate coming into the system. The problem with a purge, of course, is we're also losing some of our reactants. So some A and some B leaves the system, not reacted, so that's costing us money. And so the trade-off, if the purge stream is large, we lose a lot of A and B. If it's small, then this concentration of the inert in our recycle stream is going to be large, and it'll start affecting the reactor because it's essentially is lowering the concentrations of reactants, and the typical kinetics are that reaction rates are proportional to concentrations. Or the other way of looking at it, it's increasing the flow rate through the reactor, so giving reactants less time to react. So what we'll do next is look at a spreadsheet showing a process and look at what happens as we change the flow rate of the purge stream. I'm going to use this spreadsheet just to demonstrate the effect of the purged fraction on the flow rate in the recycle. Note that the molar flow rate of methane coming in, 1.2 moles per second, is equal to the flow rate of methane leaving, as it has to be, since there's no methane in the stream that has ammonia. A fraction of 0.03 is a reasonable value for this system. Let's look at what happens if we change that value. So here we're purging 10% of the stream that's recycling. And notice now what happens, the flow rate of hydrogen coming out, 21, flow rate coming in, about 75. So we're losing a very large fraction of the hydrogen and nitrogen by having this large fraction that's purged. Of course, it means we have a lower fraction that's being recycled, but that really becomes expensive to throw away so much of our reactants. Well, let's look at the other extreme, a very small fraction purged. So here only 1% of the recycle is purged, and so now the flow rate of hydrogen leaving is much smaller, slightly more than a tenth of what it was. But notice how large the methane flow rate is in the recycle stream. So a very large fraction of the total flow rate, which essentially decreases the reactor time or decreases the concentrations of reactants, which would affect the reactor, and also then we're pumping around a very large amount of methane through the system continuously. And so that's not desirable, and so the optimal is going to be a function of economics and our ability, for example, to separate hydrogen from this exit stream. Whatever value is picked, this purge stream is necessary in order to remove the methane that's coming in the system, otherwise we cannot run at steady state.